Welcome to our lecture series on GPU architectures and programming. So, in the last assignment we were discussing about GPU hardware schedulers and the definition of a warp. So, maybe we will restart from that point. So, essentially when we map kernel's launched set of threads or a GPU hardware, so we have a hierarchy of hardware schedulers which will now come into play. So, at the high level there will be one component of a hardware scheduler which will decide which thread block gets mapped to which of the SMs, and at the lower level inside each of the SMs there would be another component scheduler which will decide which of the threads of the mapped thread blocks will constitute what we call as a warp. So, a warp will essentially be a collection of such threads which execute in parallel as discussed earlier. So, this packing of threads from thread blocks to warps is something that will be decided by the lower level scheduler. And if we just relook into the SM, so we have this kind of warp scheduler sitting inside the SM, and there is the high level scheduler which is distributing blocks into SMs for execution. And so, just to summarize again what a warp is, it is a collection of 32 threads which will execute for using the SIMD instruction sequences, and the warps get mapped into the collection of SPs for execution. So, if a SM has an example 128 SPs, then it can execute 4 warps at any given time. Since one warp has 32 threads, so at any time in parallel the SM will have 4 warps proceeding through its SPs in parallel. So, here we have an example scenario where we are trying to provide a situation that okay, we have an SM where, as you can see, that we have a collection of SP cores. So, here you have in total 16 SP cores, right, and consider the situation that you have some warps progressing through this SM. So, for example, let us say warp 0, it is constituting. Now, this packing of threads into the warps is what is going to be done by the scheduler which is sitting inside each of the SMs, as we discussed, that this is the second level scheduler in the hierarchy. The high level scheduler is dispatching thread blocks to each SM, and inside the SM we have this kind of schedulers who is actually forming these warps. So, this low level SM scheduler is actually forming these warps like the form of warp 0, warp 1. So, it is kind of IDing each warp and it is deciding in each warp which are the thread indexes that should be constituting each of the warps. So, I have warp 0, warp 1, warp 2, warp 3, and they are containing threads with ID 0 to 31, 32 to 63, 64 to 95, so on and so forth, and they are executing the instructions that are part of that CUDA kernel under question, that instruction sequence. So, just to look into this scenario, on the right hand side we are trying to say that what is the exact sequence of these warps that are executing. So, suppose I have an instruction sequence, that is instruction 0 followed by instruction 1 followed by instruction 2. So, if in this hypothetical system, hypothetical SM, I am executing these warps, as you can see that I have a collection of these 16 cores, and each warp is containing 32 threads, right. So, assuming everybody takes a single cycle of execution for each of the instructions on the cores, there is no floating point or delay due to other kinds of complex operations. Each warp would then complete with 2 clock cycles, right, because there are 32 operations to execute in parallel for the warp, while I have only 16 cores that are available. So, the warp would technically take 2 clock cycles. So, in that way, for instruction 0 to be executed by all the 4 warps, as you can see here, I would be consuming. So, each warp is consuming 2 clock cycles. So, for this 4 warps, all of them completing instruction 0, I would require 8 clock cycles. Similarly, I would again require 8 clock cycles for instruction 1, and this way the execution proceeds here. So, again for warp 0 executing instruction 2, that would start in the 16th clock cycle. This is just an example scenario we are trying to give. So, we are trying to say that this is how the warps may get scheduled here on the core, and the number of cycles that the warp would take depends on the number of SPs that are available and also the kind of instructions that the warp is executing. Now, if I have a relook into the picture when I am considering warps belonging to different thread blocks. So, I am now considering warp 0 from thread block 0, and then warp 1, warp 2, warp 3 all from thread block 0, and then again warp 0, warp 1, warp 2, warp 3 all from thread block 1, right. So, now I have 4 warps, 4 of them belong to thread block 0, 4 of them belong to thread block 1, and if we map their execution here on an SM with 16 SP cores, just like earlier I would have each of the warps executing in 2 clock cycles. So, I would have, for example, here instruction 0 getting executed by all the warps, warp 0, warp 1, warp 2, warp 3 belonging to thread block 0, then instruction 0 executed by warp 0, warp 1, warp 2, warp 3 belonging to thread block 1, and similarly with instruction 0 completed by all the thread block warps, I have instruction 1 again getting executed for warps belonging to thread block 0, and then again I have instruction 1 getting executed for all the warps that are belonging to thread block 1. So, in this case, of course, we are having this assumption that there is a thread block scheduler which is using a round robin policy to schedule the thread blocks. Now, this is what we have as an open domain answer in the academic research papers, that people are assuming that the NVIDIA thread block scheduler is following this kind of a round robin policy, but of course, it depends on your implementation. This is the exact hardware scheduling strategy for the thread block schedulers as well as the warp schedulers is not there in the open domain, and of course, it can also be implementation dependent. Depending on different scenarios, somebody can implement the GPU hardware in a different way to have a different possible scheduling of thread blocks. From a programmer's point of view, we will always assume that the warps can proceed at their own speeds. Of course, they have to satisfy the instruction sequence requirement that is enforced by the thread. So, just looking into some more examples, here we have a very simple kernel where we can see that the kernel is a just look at the 2-line code segment on the left hand side. So, we are just computing the thread ID, and we are then using the thread ID to access some specific location of an array and simply adding the value in the location with itself and storing right there back. And on the upper part of the figure, we show that how the warps will pack the operations. So, in warp 0, I would have the locations A0 to A31 getting updated by this sequence of operations. So, this is what would get done by warp 0, and then next we would have warp 1, warp 2 and so on and so forth. And so, this is how I am just trying to show how the warps would be packing this addition operation spread over the width of the data space. Now, if we take a closer look into the corresponding PTX instructions for the actual CUDA code we have on the left hand side. So, on the right hand side we have the PTX instructions. So, the initial part of the instructions, they correspond to the thread ID computation part, and the second part of the instructions, they actually correspond to the addition operation that has been done, right. So, just take a second and have a closer look into the instruction sequence here. So, essentially as you can see that the first 5 instructions which are highlighted in blue, they are responsible for doing the thread ID calculation here, and finally in the second highlighted part, we are using this value of the thread ID to bring the content of the array at that location corresponding to the thread ID into this register here. So, essentially this is your final thread ID here, and then you use that thread ID to load the corresponding locational value using this load instruction here in R5, and then you are just adding up the content of R5 and storing into R6, and then you do a global store back into the location for the same thread ID, right. So, if we now have a look into that sequence of instructions that are executing there. So, as you can see, you have an address followed by a load operation, followed by another add operation, and then a store operation. So, for this different packing of warps like warp 0, warp 1, warp 2, these instructions, the corresponding instructions will be dispatched to the SM, the different functional units of the SM, and I mean how really would their execution be ordered. So, of course, for this the warp scheduler needs the operands for each of the instructions to be ready, right. So, there would be a mapping table from which the warp scheduler gets to know that what is the warp ID which is ready to execute. So, for example, this is a sample situation we are showing here, that warp 0 is ready to execute from this address 42, and the corresponding SIMD instruction that needs to be executed is this add as 64, which is basically the first instruction. So, if we just number the instructions for that part, so this is the first instruction. If you again have a look, the next add is the third instruction, and in between you have the load and then the store. So, the original sequence of the instructions is as I have marked in here, and as you can see, what we are trying to communicate here is the different warps may have their ready state for different possible instructions depending on what are the operands available for that instruction, whether they are ready, and also for that warp whether the preceding instructions have already executed. So, here we have one possible valid execution sequence for these instructions. So, the warp 0 would execute. So, that is your instruction with address 42. So, basically this is the warp 0 is executing the first instruction corresponding to this sum, right. So, this is the first instruction corresponding to this sum operation, warp 0 is executing that. Now, this is followed by warp 15 going to execute the fourth instruction corresponding to the sum operation. So, how can this be possible? Well, of course, that would mean that warp 15 must have already executed the previous 3 instructions corresponding to the sum operation for each part of the data space. Now, in this example, we have warp 15 being followed by warp 2. So, essentially we are saying that somehow warp 15 made progress at a higher speed, and then warp 2 executes its instruction number 3. That means, by this time warp 2 has executed its first and second instruction, and then warp 9 would be executing its corresponding instruction, which is the second instruction in the sequence. So, the idea is very simple. For every warp needs to follow the instruction sequence 1, 2, 3, 4 as has been marked for this is the first instruction, second instruction, third instruction, fourth instruction. This is a situation we are trying to show here. So, warp 0 is going to execute first instruction followed by warp 2 executing the third instruction. This is just an example we are trying to say that okay. So, when warp 0 has executed the first instruction, warp 15 is executing the fourth instruction. That would mean that warp 15 has already executed instruction number 1, 2 and 3. Now, the requirement is every warp needs to execute the instructions first, second, third and fourth in the sequence, but it is not necessary that warp 0 would execute instructions 1, 2, 3, 4 followed by warp 1 executing instructions 1, 2, 3, 4 like that. Neither it is necessary that warp 0 executes instructions 1 and then warp 2 execute instruction 1, warp 3 instructions like that. They are free to proceed depending on as and when their operands are ready. So, just like an example we are trying to say that it is not only the case that the warps would be scheduled following a specific policy. It is also the situation that the warps require the corresponding operand values to be readily available for making some progress, right. So, just to summarize that how does really warp scheduling take place in the SM. So, the warp scheduler will issue the ready to go warps, one warp instruction per cycle, and it will use an operand scoreboarding to prevent hazards. So, this is kind of the table we are trying to show here, just as an example that what are the warps which are ready to go. Now, which ones are ready to go, they actually are being computed by using a scoreboarding technique. We are not getting into too much detail of that, but of course, you need to understand that just like a pipeline here also, I need to prevent hazards. That means, I should not be executing a warp before the operands become readily available, or I should not issue a warp before the functional units become free, right. So, these are the potential hazard scenarios which needs to be prevented. For that, we will be using the scoreboarding approach. Now, the issue selection is based on round robin. There can be specific examples. There can be a round robin scheduling of warps, as an example we discussed earlier. However, that need not be the only system. It can also be based on how old is the warp active for how much time. So, depending the age of the warp, and of course, the warp has to be ready. That means, the corresponding operands need to be available and functional units need to be available. So, the scoreboarding determines whether in that way the thread is ready to execute, and essentially it is a hardware implemented table which tracks different scenarios like whether the instruction has really been fetched, whether the resources required by the instruction are really available. That means, whether the functional units are available, whether the operands are ready, and whatever is the register file that is going to be modified by this instruction, whether that can also be done. So, the scoreboard actually takes care of providing a status that whether executing this instruction would be hazard free. If so, then it would say that well, this instruction is ready to go with corresponding to operands and functional units, and then the warp scheduler will use its implementation algorithm, whether it is round robin or some other technique, to decide whether to issue that warp instruction or not. So, this is how possibly the warp scheduling would get executed. Of course, some part of it is implementation dependent, but these are the current techniques that are in actual implementations in modern GPUs. Now, the other important thing is that why really do we have this kind of warp based executions, and why do we really have this kind of multiple SPs, so many the presence of SPs in very high number inside the SMs. The reason is that you want the GPUs to tolerate long latency operations. So, when threads in one warp execute such long latency operation, for example, a read operation from the global memory, as we all know that read from the shared memory is much faster with respect to read from the global memory, which is very slow. So, whenever a warp would require any read operation from the global memory, it has to wait for a long amount of time. Now, since I have this warp scheduler internally built into the SM, so it can actually, when this warp is waiting for the operands to be available, the warp scheduler can dispatch and execute many other warps until the operands are available for the warp that was waiting, right. Also, a warp may have to wait for many other long latency operations like floating point operations, branches and that. So, overall the issue is that if a long latency operation is there, then the GPU should be able to hide the corresponding penalty. Then the way to hide the penalty is you always keep your functional units engaged by using some other warp. That is why the warp scheduler has a huge role to play in terms of feeding all the SPs with as many operations as possible by dispatching warps whenever some executing warp stalls due to a long latency operation. So, after all, one has to remember that all threads that you have which are following the same control flow, that means they are following the same sequence of ifs and same sequence of instructions, they are essentially executing the same instruction sequence. So, it does not really matter which threads execute fast or which threads inside another warp execute slow, as long as they do not have any dependency among each other, because they are all doing the same instruction sequence computation on possibly different data points on the memory. So, also a common practice in this regard is to launch thread blocks of a size that is multiple of the warp size. Now, this is something we have also discussed earlier, that if we launch a thread block with size which is multiple of the warp size, then I have all warps completely filled up with 32 threads. Otherwise, if I have a thread block size which is not a multiple of warp size, then I will have some warps which are not really full with 32 threads, and that would actually transpire to some hardwares not getting utilized while execution of that warp. And also there is this important question, like whenever a thread whenever the threads in a warp are executing a long latency operation like a global memory read, the warps can be optimized in such a way, the threads can be written in such an optimized way that the warp will always access consecutive global memory locations, so that the fetch can be done in parallel. This is known as global memory coalescing optimization, which is something we will take up later on. Now, the next thing is how to make good efficient use of thread blocks. So, we take a simple situation here. Consider some target system constraints. So, you have a maximum of 8 blocks and 1024 threads per SM, and you have the maximum number of blocks threads allowed inside block, or the thread block size, let it be 512. So, you are going to have 1024 threads per SM. You can have maximum 8 blocks, whatever you choose as the thread block size, and whatever you choose as the number of threads that you launch in total. We are restricting that one SM can handle 1024 threads, and one SM can handle 8 blocks. This is just a synthetic scenario we are assuming. This is just an example here, and let us also consider that a thread block size is limited to 512. Now, in this situation, consider different possible input block sizes for some kernel launch parameters. Consider the input block size as 8 cross 8. So, and so you have blocks per SM as 12. So, and then in this case, so if your input block size is 68 cross 8 and you have blocks per SM as 12, then you have threads per block. So, if you, since you are having this blocks per SM as 12 and input block size is 68 cross 8, so you naturally have a threads per block as 64. So, in this case our observation would be that the execution resources in the SM would be underutilized. Now, the question is, why is that so? So, in this case you are actually using the number of blocks per SM as 12, right, while you have threads per block as 64. Now, the problem would be, so since you have these 64 blocks, 64 threads per block. So, when the SM would be executing, you have in total a thread block size of 64, and in total you have 12 blocks. So, overall what would be your total number of threads that you are essentially launching? So, overall you have launched essentially 768 threads, right. So, ideally I would say that this I mean the SM could have handled more number of threads. So, execution resources are practically underutilized. Now, consider another situation where you have got this input block size 16 cross 16 2D definitions. Now, you are going to launch 4 blocks in the SM, and the number of threads that you are allowing per block is naturally 16 cross 16, which is 256. So, your total number of threads you are launching is so that essentially is the number which the SM can maximally handle. So, in this case you are using the full capacity of the SM, right. Now, consider a third scenario. Suppose where you are defining a kernel with block parameters 32 cross 32 and you are just launching one block. So, then as you can see 32 cross 32 is also 1024. So, essentially you are defining a thread block of size 1024. Now, for this example we have taken it violates the definition that I am not going to allow here for this specific example more than 512 threads per block. So, this exceeds the limit. So, this is not allowed. So, these are the typical problems that you can have while mapping a kernel to a GPU. You have to know its hardware's limitations. So, as we have discussed earlier that there are such specific limitations and you have to know them to define the corresponding different parameters spaces and corresponding launch parameters for that kernel. Now, something about different ways in which a GPU can be queried. So, the CUDA library provides you several specific constraints, this kind of constructs using which from your program you can actually figure out what is the hardware configuration of the target GPU. For example, in your program you can use this function called CUDA get device count to give you the number of devices in the system. You can use this function called CUDA get device properties which again would return different possible property values for some particular device in the system. Now, why is this important? Because as we discussed earlier, your program's kernel's launch parameters may be decided based on these different properties that you get, and also I can have so that would mean that when I write my CUDA kernel, I would have the parameters of the kernel, maybe certain access expressions in the kernel in terms of variables which would get initialized based on the different CUDA device properties that I can unearth through this kind of library function calls. So, with this we will conclude this lecture, and from the next lecture maybe we will take a deeper look into the different querying different ways in which device properties can be queried. Thank you.